Okay, so 2.2, we're looking at the difference between two different types of reasoning, inductive and deductive reasoning. Okay, so this exploration is kind of helping us understand the inductive reasoning part, writing conjecture about the pattern. Conjecture is basically just you observing something and making a prediction. That's basically what you're looking at here. So we're trying to figure out the 10th one in this pattern. So for A here, what we notice is the little dot here is in this corner of the triangle. Then on 2, it's in the left corner. Then on 3, it's in the top corner, and then it just keeps doing that, keeps rotating around, every single time. So basically, if you start here at 1, and this is 2, 3, 4, 5, 6, 7, 8, 9, 10, the 10th one, you're back here at the same spot you are on 1. So you can see that that would be what it is. The 10th one is looking the same as number 1. And it just says the circle is rotating from one vertex in the triangle to the next in a clockwise direction. So you want to write down, that would be your conjecture, your prediction, or what's happening on this. B is also not too bad. It's a coordinate plane, and you have quadrant 1 through quadrant 4. So this is 1, 2, 3, and 4. But the way this kind of goes around here, it goes from 1 to 4 to 3 to 2 back to 1. So that's what you can see there. 1, then 4, then 3, then 2, and then back to 1. And so if it's in 1 and 3, it's going to be a curve. You can see how it's curved here. Then it's curved this way. If it's in 2 and 4, it's going to be a straight line segment going down. So a straight line segment going down like that. And so you can kind of figure out if it's going to be, so this is 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. The 10th figure is going to be back in quadrant 4, which is always a line segment going straight down. So it should look like the second one here. That's the way it should look, and you can see that's what's happening. This is a really big, long explanation. You can definitely explain it a lot simpler than that about kind of what I just said. Now, letter C is perhaps the harder one to see what's going on letter C. But basically, you have 2 triangles in the first one here, then 2 circles, then 2 squares. And then it just keeps doing that every time. Back to 2 triangles, 2 circles, 2 squares, 2 triangles, and so on, So you could figure out your 10th one, which one you're going to have 2 of on the 10th one. But sometimes your 2 is on the right side, sometimes it's on the left side. And so that kind of is dependent on the one before it. So if you look at the first one, we're on the right side, but then see where the circle is on this figure is on the left. So in the next one, the circles are going to be on the left. But that moved your square over here now to the right on this one. So on the next one, your squares are on the right, the 2 squares. The triangle on this one is on the left, so you have 2 triangles now on the left. Circles on the right, so the next one's going to have 2 circles on the right. And then so on. It just keeps kind of following that type of pattern. And they said it in a nicer, easier way. So basically, you can kind of figure out what it's going to happen there. And in fact, if you think of it, this number 1 is the same thing as the 7th one. So really, this would be 8, 9, 10. 10 is going to look like this. So that's what you can see. 10 is looking like this one right here, like number 4. And so the pattern alternates between the first 3 arrangements, then respective mirror images. That's a little more of a technical definition. I would just, probably set something a lot more simpler than that. And that's fine. You don't have to say it exactly the way this is written. You can just say it in your own words. So that helps us to kind of a little bit understand inductive reasoning, which is kind of looking at a pattern and making kind of a prediction about that. Let's look at number 2. So our second one here, second exploration, you're given this Venn diagram. And this is going to help us now kind of understand deductive reasoning. So it says, use the Venn diagram to determine whether the statement is true or false. Justify your answer. So I'll give you some time. Go ahead and figure out if it's true or false by looking at this. And then it says here, assume no region of the Venn diagram is empty. So even though this intersection part right here looks empty, just assume it's not empty. Assume there's stuff in there. So I'll give you some time there to work on that, and then we'll go over these answers. All right, so let's go ahead and look at our answers for these, A through G. So letter A says if an item has property B, then it has property A. Well, that would be true because B is inside of A. So if it's in B, it's also in A. So that would be true. B says if an item has property A, then it has property B. Well, that would be false because you could be outside of B, but still in property A, right? C, it says if an item has property A, then it has property C. Well, that's false because you could be over here in this side where you're not in property C's circle at all. So that's false as well. You can be in property A, but not in C. D says some items that have property A do not have property B. And that would be true. Yes, those items that are outside of property B, but still in A here. So some items outside here are not in B. So that was true for E. And then F says some items have both properties A and C, which would be true because A and C overlap right in here. So the items that are inside the intersection part would have both. So that's true. And then G says some items have both properties B and C, and that would be false. You can't be in both B and C. They don't intersect or they don't overlap at all. They are what we call mutually exclusive. And so that would be a false statement there. So what we're seeing on this one is that we're given a diagram, some concrete evidence to be able to make our conclusions with. These are not just, predictions. We're not predicting anything here. We're making a conclusion based on the diagram that's given to us. And so that's more of a deductive reasoning. If your reasoning is based on something concrete, okay, like a diagram, then that's definitely deductive. If your reasoning or your conclusion is pretty much based on like maybe just experience, something that you can't prove, then that's an inductive reasoning. So as we get into our core concept, you might want to take out your highlighter as we go through here. So this has all of the vocab that you need to know for yourself. And really the main part of this chapter, again, is just learning the vocab, learning what these words mean. Starting with inductive reasoning. So a conjecture is an unproven statement that's based on observations. A conjecture. What is a conjecture? We're doing that there on Exploration 1. We were making those conjectures, but they're unproven statements. Statements that necessarily can't be proven. So, and you're proving them based on an observation that you have. So let's just say that for the last few weeks, I'm going to show you this calendar. This was back in August, though. But let's say for these 3 weeks here, week after week, for lunch, you kept seeing ketchup while you're standing in line. And then when you got in there, they had hamburgers. Okay? You saw that on the 7th, on this Wednesday. The next Wednesday, you see the same thing, the ketchup, and you're having hamburgers again. And then on the 21st, the next Wednesday, you see ketchup and you're having hamburgers again. So when you get to the 28th, that next Wednesday, and you see ketchup, can you kind of think that you're probably going to have hamburgers again? Probably, right? That's a conjecture. You're conjecturing you're going to have hamburgers. Every Wednesday, basically the conjecture is, well, Wednesday we're having hamburgers. Because that's been the pattern. And I've observed the ketchup every single Wednesday, and we always have hamburgers then. So when you see the ketchup, that must mean you have hamburgers. Okay? That's what inductive reasoning is. That you're making that assumption, right? Can you prove that, though? Can you prove that you're going to have hamburgers? No, you can't prove it. There's no way to prove it. It's just experience. So you're making a statement. Wednesday we have hamburgers. When we see ketchup, we have hamburgers. That's something you can't prove. That's just based on observation. So that's what inductive reasoning is. And here it is again right there. You want to highlight this. Inductive reasoning is when you find a pattern in specific cases and then write a conjecture for a general case. So the specific case was every Wednesday, Saw Ketchup had a hamburger. Saw Ketchup again had a hamburger. Those are specific cases. But then you made this general case that, well, Wednesday we have hamburgers. That's the general case. Or when we see ketchup, we have hamburgers. Something like that. Now, a counterexample is the next thing to say here. Because in order for inductive reasoning to actually be true, you have to show, in order to show that your conjecture really is true, which is inductive reasoning, in order to show that's true, you must show that it's true for all cases, all the time. So, it's hard to show that an inductive reasoning is true because there's an sometimes infinite amount of cases. It's easy to show that inductive reasoning is false because all you need is one counterexample and it destroys the whole argument. One time when you see ketchup and there's not hamburgers, that one time destroys the whole thing. So that's what counterexample is. It's a specific case for which the conjecture is false. So let's just say we go back to our calendar here and we see on the 28th, that Wednesday, we see the ketchup. But we get in there and there's hot dogs. There's no hamburgers. Hot dogs. Well, that just destroyed our whole argument. See, our conjecture was disproven. And so that's a counterexample. The fact that that specific case, when we saw the ketchup and had hot dogs, it blew our whole argument out of the water. And so that was it. That was a counterexample. Yeah, you just need one counterexample to disprove the whole inductive reasoning. So that's why it's easy to destroy inductive reasoning. It's hard to prove it, though. Let's go to the other type of reasoning now, deductive. Deductive, like we were talking about with that diagram, had hard evidence, hard concrete evidence, and so that's what it uses. Deductive reasoning uses facts, it uses definitions, it uses accepted properties, it uses laws of logic to form a logical argument. So we understand facts, okay? We know what facts are, okay? We know what definitions are, like we've talked about the definition of collinear points. Those are points that lie on the same line. That's a definition of what collinear means, points that lie on the same line. Yeah, that's a definition. We can use that with deductive reasoning. Accepted properties. Well, we know about the distributive property. We could use that property with deductive reasoning. Okay, so any kind of properties are accepted. Laws of logic. Now, the laws of logic might be a little bit new, so that we might want to have a little bit of explanation. So that's why it talks about the laws of logic down here. There's two of them, law of detachment and law of syllogism. I'm not going to spend a lot of time with the detachment one. In fact, we're not going to really worry about that one much at all. It just says if the hypothesis of a true conditional statement is true, then the conclusion is also true. Okay, that should make sense. It should pretty much make sense. The syllogism one, though, this is the one I wanted to spend a little more time on because this law of syllogism actually matches with a property that we have to become very familiar with called the transitive property. We're going to see it in 2.4's lesson. That's when we're first introduced to this thing called the transitive property of equality. And so basically what it does is this. Here's a law of syllogism, but it's in essence, it is the same thing as this transitive property that we're going to come to know. It says if hypothesis P, then conclusion Q. The second one says if hypothesis Q, then conclusion R. And the third one is if hypothesis P, then conclusion R. So basically, if these two statements are true, then this statement would have to be true. And what I kind of like to think about this here, basically, P is here, R is down here. Or actually, I should say it's here, really. First time we see R. So you have P and R there. I think of this kind of like the friends property. So basically, if P knows Q, and P's friends with Q, and Q knows R is friends with, or Q and R are friends, then that automatically makes P and R also friends. It's kind of like the thing that the statement that we like to say, any friend of yours is a friend of mine, right? You've heard that before. And so it's like, you know, any friend of Q is a friend of mine. So if R is a friend of Q, then P and R are going to be friends. You know, they're going to be together. So that's why you see down here, if P, then conclusion R. And so that's going to be something that we're going to see over and over again with a transitive property in all different situations. We're going to see it with angle measures, with segments, with even just, you know, anything, really, any numbers, you know, we see. We're going to use this transitive property, this kind of friends property. Any friend of yours is a friend of mine kind of property. And that's what this law of syllogism is about. It's a law of logic. It's just logical flow of argument. If these two are true, then that makes this one true. Okay? So let's go into our extra practice now. So extra practice 1 through 4, this is now about the inductive reasoning. You're going to look at a pattern and then see if you can predict, you know, draw a conclusion from that, predict the next either number or letter or shape. So I'll give you some time to work on that. So work on 1 through 4. I'll give you a couple minutes to look at that and see if you can figure out what's the next two. It says next two ones. And then we'll go over 1 through 4. Okay, so let's go over this 1 through 4. So number 1, you got the numbers here, 20, 19, 17, 14, 10. As you can see there, 20 to 19, there's just 1 going down. 19 to 17, that's 2 going down. Then there's go down 3, then go down 4. So the next one should be going down 5. So that's going to be 5. And the next one after that should go down 6, which would be a -1. So 5, -1 will be your next two numbers there. And so as I was mentioning, number 2, this one you notice it's the prime numbers. These are prime numbers. 2 is your first prime number. 3 is the next prime number. 5 is the next one. Remember, prime number is just a number that only has 2 factors, just 1 and itself. So 4 is not a prime number. That's why it's not listed. 6 is not a prime number. It's not listed. 8, 9, 10. Those are not prime numbers. They're not listed. So the next prime number after 11 would be 13. Right? 13 just has 1 in itself as factors. The sign of 13, as you can see here, they're changing from positive to negative every time. So the sign of 13 should be a negative because 11 is positive, so it should be a -13. For the next one, after that one, the next prime number is 17, and it should be a positive for that one. Number 3 here with these letters, you can just see that's basically it's the alphabet, but you're just skipping 1 every time, right? C, skip D, E, skip F, G, skip H, and so on. So K, skip J, and then you're going to see the next one. Or no, sorry, K, yeah. So the next one should be M. So J, K, L, M, right? Skip L, then M. So M is the next, skip N, then O will be the next one after that. And then number 4 should be pretty easy to see. The next one should have basically an extra box inside here, and the one after that should be have an extra 2 boxes inside. So that's probably pretty easy to see those little squares there. So you can draw those next 2 the way they're supposed to be drawn. Just do a little quick sketch of those. Alright, let's go ahead and look at number 5 and 6. It says, make and test a conjecture about the given quantity. So we're talking about inductive reasoning with this when it's talking about making and testing a conjecture. Conjecture is always with inductive reasoning. And so number 5 says, the sum of 2 negative integers. And I put down is question mark, is what? That's really what you're trying to figure out there, okay? So what would you're making a conjecture is the conjecture is what? If you're observing, what are you observing when you have the sum of 2 negative integers? What's your observation? That's really your conjecture. Sum of 2 negative integers is what? So you can kind of think about 2 negative integers, like -1 and -2, If you add those together, think about the answer you get for that. What do you observe about that answer? Okay, well, what you should observe about that answer is that the answer is going to be a negative integer. Every single time, the sum of two negative integers is going to give you a bigger negative, right? That's what happens. We know that to be true. And when you add two negatives, you're going to get a bigger negative. It's always going to still be negative. And so you can use any sample answer here if you want to just write one of these, or you can write the one I said, -1 plus -2 equals a -3. You can say that as well. But basically, you could just say, is a negative integer. You can say that. You don't have to rewrite the sum of two negative integers. You can just say the is what part. Is what is question mark is a negative integer. 6 says the product of three consecutive non-zero integers, and I put the is question mark. You might want to put that there so you know, okay, we're looking for what do you observe when you multiply, that's what product means, three consecutive non-zero integers, so it just can't be 0. So consecutive means one right after the other. So like 1, 2, 3, if you multiply 1, 2, 3, you get 6, right? Now you might not be able to observe anything just yet. You might need to do that a few more times to figure out what the pattern is, what you're doing there when you get, three consecutive. You just can't do like 0, 1, 2, 3 or 0, 1, 2. You can't have a 0 in there. You could be even negative numbers. You could do -4, -3, -2. You can multiply those together. When you multiply three negatives, you will get a negative answer, but 4, 3, 2, that's going to give you, what, 24, -24? So what you might start to see about this as you do that a few times is you're going to see that you're always going to get an even integer. You will always get an even integer. The product is an even integer. So is what? Is an even integer. Okay, so that's what it's going to be. The product of three consecutive non-zero integers is an even integer. It might be positive, it might be negative, but the fact remains it's going to be even. And so you can use use one of these here. You can use one of these or use the ones I said, like 1, 2, 3 equals 6, that kind of thing. You might want to write a couple of them down just to show that, you're getting a negative, an even integer. Now, 7 and 8 now are talking about a counterexample. So we're still dealing with inductive reasoning, okay? Because counterexamples are the torpedo that blows the inductive reasoning argument out of the water, right? That's what we learned. Counterexample is showing that the conjecture's false. So number 7, here is the statement. Here is the conjecture, we might say. Here is the inductive reasoning on 7. If n is a rational number, then n squared is always less than n. It's a strong statement. When they use the word always, it's always going to be less. It's every single time, it's always going to do this. It's kind of like our hamburger and ketchup thing. You see the ketchup, you're always going to have a hamburger. Always, every single time. I mean, you never put ketchup on a hot dog. So it's a strong statement to make these statements, to make these claims or, predictions. So what would be a counterexample to that? Well, just try any number. Let's try 2. Okay, if n was 2, and we said, okay, n squared is 2 squared. So is 2 squared less than 2? No, 2 squared is 4, right? We know 2 squared is 4. Is 4 less than 2? No. That would be a counterexample. You can use that. This one says a different number. This one says 3 over 2. They used a fraction, 3 over 2. So they're saying n is 3 over 2, and if you square it, that's 3 over 2 times 3 over 2, you're going to get 9/4. And 9/4 is greater than 3 over 2. That's a counterexample to that statement, to this inductive reasoning. Really, you can almost use any number. Like I said, you could use 2. So if you said, okay, n is equal to 2, that means that n squared is going to be 2 squared, which that equals 4. And we know 4 is greater than 2. So the n squared here is greater than the n. This is saying that n squared is always less. So it disproves it. You just need one counterexample, though, to disprove the argument. 8 says line K intersects plane P at point Q on the plane. Plane P is perpendicular to line K. So basically, it would be if you thought of the, like this flat screen right here as it, and you have a line going straight through it at a perfect 90-degree angle. That's what it's saying is always going to happen. Well, how do you disprove that? Well, just change it to be not a 90-degree angle. So it could look like this. You could draw a plane. There it is. So you can draw a plane like a parallelogram right there, and a line just not going through at a right angle. That's going through at a slanted angle. So that would be a counterexample. It's still going to go through at point Q, but it's not a perpendicular. See, it says plane P is perpendicular to line K. And this would be a counterexample. It's a plane P is not perpendicular to line K. There's a counterexample to that. So go ahead and just draw that for number 8. Do a little quick sketch of that one. That will disprove 8. Okay, so for these last few problems here, we're not going to spend any time with 9 and 10. Not going to worry about the law of detachment. That's not going to be tested on at all. The syllogism, though, is one that you need to get to kind of understand just because of the transitive property that we're going to be using, in the next basically several lessons in this chapter and then continue in all the other chapters. We keep using this transitive property. So let's take a look at 11 and 12. It says, if it does not rain, then I will walk to school. If I walk to school, well, then I will wear my walking shoes. So basically what we can conclude from this, if this is true and this is true, then if it doesn't rain, then I'm going to wear my walking shoes. That's what we can conclude. That's what we would say here. It says, use this law of syllogism to write a new conditional statement, a third conditional statement, because these are all conditional statements in if-then. We can write a third one with, if it does not rain, then I will wear my walking shoes. That's basically what they're doing there for number 11. And then for 12, if x is greater than 1, then 3x is greater than 3. Well, if 3x is greater than 3, well then 3x squared is greater than 9. So if these two are true, then we can write a third conditional statement that is also true with if x is greater than 1, then 3x squared is going to be greater than 9. And that's the law of syllogism, which I said is also almost identical to what the transitive property is. All right, so that concludes the 2.2. We're going to go on, and then the next lesson, I'll see you there on 2.3.